Chapter 12. There are many original and exciting ways to produce energy that may help to reduce our dependence on fossil fuels. This chapter will look at the energy, power, and their impact on climate change. Energy is the ability to apply a force over a distance, and a force is a push or pull on an object. Imagine water from a river pours onto a water wheel and strikes its paddles. Before the water begins to flow, the water wheel is still, but the wheel begins to turn when the force of the moving water hits its paddles. The force of the water on the paddles moves them around and around over a distance. According to our definition, the moving water is a source of energy, and we can say that the energy of this moving water as it strikes and turns the wheel is converted to or transferred to the energy of the moving wheel. Energy can be transferred from one form to another. As illustrated below, the energy generated in a nuclear power plant is converted to electrical energy, which is used to power a blinder. The blinder converts the electrical energy to mechanical energy, the energy of work being done, such as blinder blades turning. The protein smoothie made in the blinder provides chemical energy in the form of food to the person who drinks it. The person converts that chemical energy to mechanical energy and moves boxes onto a truck. The truck moving the boxes stops for diesel fuel, which contains chemical energy. The truck burns the fuel and converts its chemical energy into the mechanical energy of moving wheels and turning axles. Finally, energy from the sun shining on a solar panel is converted to electrical energy, which is used to power emergency warning lights on the highway. Power is the amount of energy generated or used in a specific period of time. The wheel rotates at a rate of 100 revolutions per minute, has more power than the wheel rotates at a rate of 10 revolutions per minute. The metric unit for power is watt, designated with capital letter W. A watt is the number of joules of energy transferred per second. For example, a 100-watt light bulb uses 100 joules of energy every second. Old-fashioned incandescent light bulbs convert only about 2% of their electrical energy to light. The remaining 98% becomes heat, or thermal energy. All of the electrical energy goes into a light bulb, leaves as light or thermal energy. That's because one form of energy can be converted to other forms of energy, but energy always persists. It does not just disappear. The behavior of energy and power are governed by one fundamental absolute law of nature, the first law of thermodynamics, which states that energy cannot be created or destroyed. Over the last 200 years, there has been a radical shift in energy use in the United States. The diagram on the left shows how the US has shifted its use of energy resources over the past 200 plus years. In the 1700s and 1800s, the primary source of energy in the US was wood. Coal became the dominant energy source in the early 1900s, until it was surpassed by petroleum and natural gas in the 1950s. Coal had a resurgence when the technology was developed to create electrical energy in coal-fired power stations. Today, petroleum, natural gas, and coal are still dominant, while nuclear energy, hydroelectric, wind, and solar lag far behind. Since the 1950s, petroleum, natural gas, and coal have dominated the US energy profile. They are examples of fossil fuels. Fossil fuels are derived from organic matter, including plant and animal fossils, that have decayed over eons to make a mixture of carbon-based molecules. Within Earth, those carbon-based molecules became compressed over millennia and formed deposits of coal and oil. Examples of molecules that you would find in various types of fossil fuels are shown here. The atoms in the molecules are connected by lines, so we know that they are molecules with covalent bonds. All the molecules here are hydrocarbons because they are comprised of just two elements, carbon and hydrogen. Hydrocarbons come in different shapes and sizes. They can have chains that are straight or branched. They can even form rings. Fossil fuels, including natural gas, crude oil, and coal, are mixtures consisting mainly of hydrocarbon molecules. Refineries separate fossil fuels into usable fractions. Crude oil is a mixture of hydrocarbons that is separated by fractionation. In the fractionation process, the mixture of crude oil is heated to a temperature that converts most of the hydrocarbon molecules in the mixture into the gas phase. As the mixture travels up, it moves into progressively cooler regions of the column. When a given hydrocarbon molecule reaches the temperature at which it condenses, it returns to the liquid phase and is removed from the column along with other hydrocarbons with a similar carbon count. Fractionating columns are contained within towers at oil refineries. Towers like these can be 30 stories high. Hydrocarbons with the lowest boiling points will travel the furthest up the fractionating column before being recondensed to liquids. Hydrocarbons with more carbon atoms generally have higher boiling points, because the more carbon atoms a molecule has, the more surface area the molecule has, the more it interacts with neighboring molecules like itself. As a result, a higher temperature is required to disrupt interactions between molecules. Fossil fuels are fuels because energy is released when the fuels undergo a combustion reaction. For a combustion reaction to occur, oxygen must be present. In the presence of oxygen, the molecules in the fossil fuels combust to make carbon dioxide and water. An example of the combustion of natural gas, methane, is shown below. Gasoline is a mixture of hydrocarbons that have on average about 6 to 8 carbon atoms per molecule. When gasoline combusts, same as in the combustion of natural gas, carbon dioxide, water, and lots of heat are produced. In a car engine, the heat produced by combustion causes the gases it produces to expand quickly, and the pressure in the engine sharply increases. This pressure pushes the pistons. The pistons turn a crank. The crank turns the axle, and the tire starts to roll. A car's fuel economy is related to its power. A car with a lot of power can transfer the chemical energy of the fuel into the mechanical energy of turning the wheels in a short amount of time. A car's power is usually expressed in the units of horsepower, where 1 horsepower is equal to about 746 watts. Fuel economy is the distance cars can travel on a given volume of fuel. In the United States, we typically express fuel economy in units of miles per gallon, or mpg. Different cars can have very different fuel economies. For instance, the 2013 Smart Fortwo has a fuel economy of 34 miles per gallon, and the 2013 Dodge Viper SRT10's fuel economy is only 12 miles per gallon. The climate of our planet is changing. Measurements show changes in the prevalence of droughts and extreme weather, the amount of precipitation, and the number of heat waves, among other things. These changes are known collectively as climate change. Our planet is getting warmer at a faster rate than it has warmed in the past due to human activities, especially the burning of fossil fuels, including coal, natural gas, and petroleum. The burning of fossil fuels makes the planet warmer because carbon dioxide is released into the atmosphere and traps heat from the sun. The light from the sun that passes into Earth's atmosphere can be absorbed by the surface of Earth, or it can escape back into space. Some of that energy is trapped by certain gases, such as carbon dioxide, are called greenhouse gases that help to heat Earth's atmosphere. This natural process is known as the greenhouse effect. It maintains Earth's temperature in a range that can sustain life. However, the enormous amounts of carbon dioxide produced by the burning of fossil fuels causes an enhanced greenhouse effect, where excess heat is trapped within Earth's atmosphere, and the planet becomes unnaturally warmer. The figure below shows data about global warming, the increase in temperature of Earth as a result of human activity. The data supporting the evidence in the figure have been collected by scientific agencies. Some data rely on the temperature measurements of the ocean or the Earth's surface. Others rely on satellite and atmospheric measurements. Regardless of the data source, we can conclude that Earth has been getting warmer. In fact, the warmest 10 years on record all occurred between 2000 and 2012. Evidence that the climate is changing because of these warmer temperatures is remarkable and well documented. There is evidence that sea levels has risen, ice sheets have been shrinking, and the ice in the Arctic has become thinner. Glaciers are disappearing worldwide. Despite overwhelming evidence, though, some people still claim that climate change is not taking place. But there is no credible peer-reviewed data to show that climate change is not due to global warming. Atmospheric carbon dioxide levels reached 400 parts per million in 2013. Throughout the history of our planet, carbon dioxide levels have gone up and down, but they have stayed mostly in the 180 to 300 parts per million range. The 300 part per million mark was passed before 1950s, and the next milestone was the 400 part per million mark. The 400 part per million mark was a big deal because we reached it very quickly, much faster than scientists expected. Can humans easily reverse the effects of global warming? Unfortunately, the answer is no, not easily. Even if we reduce carbon dioxide emissions in a radical way right now, climate change will continue for hundreds or thousands of years. In addition to carbon dioxide gas, methane, carbon monoxide, and dinitrogen monoxide also contribute to climate change. Shifting away from fossil fuels will require overcoming many challenges. We have overcome issues such as when cars first replaced horses on the road. New conflicts over transportation arose. When seatbelt laws was enacted, the auto industry resisted attempts to regulate the safety of its cars. During the oil embargo of 1973, gas stations often had no gas to sell, even with an increase in gas prices. At the time, the average fuel economy was below 15 miles per gallon. In the wake of the oil embargo in 1975, the U.S. Congress passed the Corporate Average Fuel Economy Laws, aka the CAFE laws, that required a doubling of fuel efficiency within 10 years to a value of 27.5 miles per gallon. Automakers predicted a certain doom for the auto industry, but within 10 years, the industry persevered and the new standard was met. In 2010, the Obama administration passed two new CAFE laws. The laws mandate that the average mile per gallon values must increase from 25.3 miles per gallon in 2010 to 34.1 miles per gallon in 2016 and to 54.5 miles per gallon by 2025. Wind is an energy resource that can provide power to people who happen to live in the windy places. The island of Utsira in Norway uses wind energy for power. The island's wind turbines have been producing more electricity from the wind than the inhabitants can use. To solve this problem, the island added an electricity generator that splits water according to the following chemical equation. The process of splitting water into hydrogen and oxygen using an electric current is known as electrolysis. The hydrogen gas that is produced via electrolysis is stored for later use. The hydrogen gas produced in the previous example is a fuel, because when hydrogen molecules react with oxygen molecules in a fuel cell, energy is produced. You can think this is the same way that energy is produced when gasoline reacts with oxygen in a car engine. A fuel cell is a type of electrochemical cell that produces electrical energy from certain chemical reactions. In a fuel cell, two reactions are occurring at the same time. In one reaction, electrons are being produced. In the other reaction, electrons are being used. These reactions are called half reactions because they must be paired. You can easily recognize half reactions because they always show electrons as either a reactant or a product. Let's take a closer look at the half reactions. Oxidation half reactions have electrons on the product side. Electrons are produced as shown below. Oxidation is a loss of electrons. In this half reaction, hydrogen molecules are oxidized to make protons, or the H+ ions, and electrons. Reduction half reactions have electrons on the reactant side. Electrons are consumed as shown below. Reduction is a gain of electrons. In a fuel cell, the oxygen molecules are reduced when it combines with protons to form water as shown below. Oxidation and reduction half reactions must be paired together to make a whole reaction, because one must occur for the other to happen. Oxidation half reactions produce electrons, and those electrons are then used up in a reduction reaction. An oxidation reduction, or simply redox reaction, is what we get when we combine them in a way that cancels electrons on both sides. To see how this is done, consider the two half reactions that we looked at in the previous slide, including different numbers of electrons. To make them equal, we multiply everything in the oxidation reaction by a factor of 2 to get this equation here. Now that each of our half reactions has 4 electrons in it, we can add them together to make a redox reaction. We do this by combining everything on the left side of each half reaction and everything on the right side of each half reaction and putting them into a single new chemical equation. Then we cancel anything that appears on both the left and the right side of the chemical equation. After canceling out the protons and the electrons, we have a redox reaction that summarizes the chemistry that takes place in a fuel cell. The figure on this slide is a schematic drawing of a fuel cell. The hydrogen molecules flow into the cell from the left, where they are converted to protons at the anode through an oxidation half reaction. The electrons produced from the oxidation half reaction at the anode leave the cell as electric current, aka electricity. Current flowing at a specific rate through the wire can provide electrical power to a device that is powered by electricity. The flow of electrons returns to the fuel cell at the cathode, which is where the reduction half reaction takes place. This is where protons, electrons, and oxygen molecules come together to form water. Fuel cells seem like a great way to generate energy and emit zero carbon dioxide. What are the drawbacks? Hydrogen gas is hard to come by. It is rare in nature and is not easy to make or store. In addition, the electrolysis of water requires enormous amounts of electricity, and right now, there are no other commercial viable ways to make hydrogen. As the world's population grows, so does the world's demand for energy. That energy must come from somewhere. Right now, most of it comes from burning fossil fuels. In addition to the pollution caused by fossil fuels, its supplies are also limited. It is estimated that our fossil fuel reserves will last for another 75 to 500 years. However, there is one virtually unlimited source of energy, the sun. Ultimately, it is the sun that gives us the energy we need to sustain our bodies. Through the extraordinary process of photosynthesis, plants convert the sun's energy to chemical bond energy. Through photosynthesis, plants are able to combine sunlight, carbon dioxide, and water to produce glucose and oxygen. The glucose becomes food for the plant, and the oxygen is released into the air. That oxygen becomes part of the supply of oxygen that humans breathe. Therefore, plants are important sinks for carbon dioxide and producers of oxygen molecules. Solar energy is collected using solar panels that are made up of photovoltaic cells, a type of device that converts light energy to electrical energy. Most photovoltaic cells are comprised of sheets of silicon. When silicon atoms form silicon-silicon bonds, these bonds extended in a crystalline solid, like carbon does in diamond. Some of the valence electrons in the silicon atoms in the network are occasionally able to move across a gap from a lower energy level to a higher one. This jump to a higher energy level requires an outside source of energy, such as light energy. When silicon in a photovoltaic cell is exposed to sunlight, some of the electrons absorb that solar energy and are prompted to a higher energy level. An electron moving to the higher energy level leaves behind a hole in the crystalline solid, and because this hole represents a missing negative charge, we consider the hole to have a positive charge. The positively charged hole attracts an electron from someplace else in the network, and that electron, as it migrates to the hole, leaves a fresh hole behind its original location. As a result, there is a great deal of traffic within the silicon network. As we learned earlier, moving electrons constitute an electric current. Thus, silicon is used in photovoltaic cells because it can conduct an electric current when light shines on it. We refer to silicon as a semiconductor because it conducts an electric current only under these specific conditions. On the top of the photovoltaic cell is an anti-reflective coating. This minimizes the reflection of light off the cell's surface, so that as much light as possible goes into the cell. Under the coating is a grid of electrical wires and contacts that carry electric current generated within the cell. Under these wires is a specially treated form of crystalline silicon. When light strikes this crystalline silicon, electrons flow to the front contact and then out of the cell. That electric current can be used to power a device, or it can be stored in a battery. Rechargeable batteries are electrical chemical cells that can be used to store solar energy. Like fuel cells, batteries produce electricity based on two half reactions. The reduction half reaction uses a mixture of metals, represented by the letter M. In the oxidation half reaction, a nickel ion is oxidized and one electron is produced. These two half reactions are physically separated within the battery so that the electrons flow between the two halves of the battery. The nickel metal hydride battery is special because it is rechargeable. A rechargeable battery uses chemical reactions that are reversible as they can go in either direction. They are a good choice for use in electric cars. Electrical energy flows into the battery to charge it. When the battery is fully charged, the car can be taken for a spin. In a solar home, the photovoltaic array on the roof collects solar energy, converts it to electrical energy, and sends that energy into the home. Some of the energy powers the home during the day, and the rest is stored in rechargeable batteries. Homes can also be connected to electrical grid and sell electricity to the utility company through net metering. Solar energy can be used anywhere the sun shines. In general, in places that get 4 or more peak sun hours per day, solar power is an obvious alternative. In the solar industry, a peak sun hour is 1 hour of sunlight at a power of 1000 watts shining on 1 square meter of Earth. In the US, the desert Southwest and Hawaii receive the most solar energy per day. One common criticism of solar power is the inefficiency of solar panels. The best commercially available solar panels have an efficiency of about 20% of the light that shines on them into electrical energy. Currently, a massive research effort is aimed at increasing the efficiency of solar panels, and the best experimental panels now have efficiencies of more than 50%. As efficiencies increase, homes and buildings in more and more places on Earth will be able to use solar energy as a sole source of electricity. Question 1. What is the ability to apply a force over a distance? A. Power. B. Velocity. C. Watts. D. Energy. Please pause your video here. The correct answer is D. Energy. This question asks the definition of energy, which is the ability to apply a force over a distance. Question 2. What was the largest source of energy used in the United States in 2012? A. Petroleum. B. Wind. C. Coal. D. Nuclear. Please pause your video here. The correct answer is A. Petroleum. Refer back to the figure in slide number 6 for answer. Question 3. Which hydrocarbon has the lowest boiling point temperature? A. Octane. B. Hexane. C. Butane. D. Decane. Please pause your video here. The correct answer is C. Butane. Hydrocarbons with more carbon atoms generally have higher boiling points. Or to say that, the hydrocarbons with the least number of carbons will have the lowest boiling point. Therefore, in choice A, octane has 8 carbons, hexane has 6 carbons, butane has 4, and decane has 10. Therefore, C is the one with the least number of carbons. Question 4. What happens in a fossil fuel combustion reaction? A. Energy is absorbed and carbon dioxide is consumed in a combustion reaction. B. Energy is released and carbon dioxide is consumed in a combustion reaction. C. Energy is absorbed and carbon dioxide is produced in a combustion reaction. D. Energy is released and carbon dioxide is produced in a combustion reaction. Please pause your video here. The correct answer is D. Energy is released, carbon dioxide is produced in the combustion reaction. The combustion reaction produces carbon dioxide, water, and lots of heat. Question 5. What is the greenhouse effect? A. The Earth emits infrared energy and the greenhouse gases trap some of the thermal energy, keeping the Earth warm enough to sustain life. B. The Earth emits ultraviolet energy, and the greenhouse gases trap some of the light energy, keeping the Earth warm enough to sustain life. C. Greenhouse gases absorb incoming infrared energy from the sun, keep the Earth warm enough to sustain life. D. Greenhouse gases absorb incoming ultraviolet energy from the sun, keeping the Earth warm enough to sustain life. Please pause your video here. The correct answer is A. The Earth emits infrared energy, and the greenhouse gases trap some of the thermal energy, keeping the Earth warm enough to sustain life. First of all, you need to realize that the energy involved in the process have nothing to do with ultraviolet light, the UV light. Therefore, we can rule out choice B and choice D. So we only have A and C left. A, the focus is the gas traps the energy. In C, it says the gas absorbs the energy. So greenhouse gas doesn't absorb any of the energy. It only traps the energy to keep it warm. So C is out to give you the correct answer as choice A. Question 6. Which molecule is not a greenhouse gas? A, ozone. B, oxygen. C, dinitrogen monoxide. D, carbon dioxide. Please pause your video here. The correct answer is B, O2, oxygen gas. Almost all living things need oxygen to survive. In addition to the 3 listed greenhouse gases here, carbon monoxide is also a greenhouse gas. Question 7. Select the oxidation half reaction. A, copper plus 2 electrons turn into copper metal. B, oxygen plus 4 electrons turn into 2 water molecules. C, zinc metal turns into zinc plus 2 ion and 2 electrons. D, 2H plus ions plus 2 electrons turn into hydrogen. Please pause your video here. The correct answer is choice C. Oxidation half reactions have electrons on the product side. Reduction half reactions have electrons on the reactant side. So therefore, C is the only one with electrons on the product side. That is the correct answer. Question 8. Add together the following half reactions to determine the overall net reaction. Perform cancellations as necessary. The equations are as following. 2H plus 2 electrons turn into H2. Nickel turns into nickel 2 plus 2 electrons. Choices are A, H plus nickel turn into H2 plus nickel plus. B, H plus nickel plus turn into H2 plus nickel. C, 2H plus nickel 2 plus turn into H2 plus nickel. D, 2H plus nickel turn into H2 plus nickel 2 plus. Please pause your video here. The correct answer is D. To work the problem out, we're first going to add these two equations together. So on the left hand side, we have 2H plus 2 electron and nickel. On the product side, we have H2, nickel 2 plus, and 2 electrons. We're going to cross out the species that's the same on both sides. That's the 2 electrons. Then we're going to rewrite the equation as 2H plus nickel and H2 plus nickel 2 plus. That's the choice D. Question 9. Which type of device converts light energy into electrical energy? A, photovoltaic cells. B, solar turbines. C, hydroelectric cells. D, efficiency turbines. Please pause your video here. The correct answer is A, photovoltaic cells. Question 10. Fill in the blank. One limitation of solar energy was the low efficiency of solar panels, but massive research efforts have increased the efficiency of new solar panels to greater than blank. A, 35%, B, 50%, C, 75%, D, 90%. Please pause your video here. The correct answer is B, 50%. Refer back to slide number 36 for answer.